Good evening, good morning, good afternoon, whatever time you happen to be watching it. So here we are again, AP Calculus. Going to start looking at finding limits analytically. So we already started to looking at limits both from a numerical perspective, so doing it in tables, then looking at limits and analyzing them by staring at the graph. And now we're going to look at it by trying to solve it algebraically or analytically. So before we get into that, so there's going to be a series of about 3 videos, kind of breaking down what to look for, techniques that we're going to want to use to help us figure it out without having to go through the process of creating the table or using the graphs. Now, if at any time any of these techniques will work for any of the problems, it's just a matter of which one you feel is going to be the easiest, the fastest for you in particular to do it. So if at any time you feel stuck on any one particular question, always know that you have the other ways of solving it to go back to. So don't feel like you got to always solve it using it one way. All right, so we're going to go over to the whiteboard so we can start talking about today's particular concept, which I want to talk about, which is indeterminate and undefined. Okay, so let's address this term of indeterminate. So and we had one in the examples. So when we say indeterminate, we're talking about when we get a result like 0 over 0 or infinity over infinity. Now, it could be negative infinity over negative infinity, so just in general, infinity over infinity. Now, there are other forms of indeterminate, but for AP Calculus AB, we're only going to deal with these two in particular. So I'm seeing this division of 0 over 0 or infinity over infinity. This is completely different from saying something is undefined. So undefined is a non-zero number divided by 0. Okay, that is not the same as saying that something is indeterminate. So we had one in our limits notes, which you saw, which was limit as x approaches 2 of x cubed over 8, x cubed minus 8 over x minus 2. Now, if I were to directly plug in 2, which we shouldn't be doing because that's not what a limit says to do, but if you were to directly plug in 2, you would have gotten, and I'm going to put a little arrow here. Let me redraw that one. There we go. All right, so I'll plug in 2, and then I'm going to get 8 minus 8 over 2 minus 2, which is my indeterminate form. Now, we saw that when we graphed this, that at 2, we have a removable discontinuity. Okay, and the term removable meaning hole in the graph. So when we have a hole in the graph, a removable discontinuity, we could see that the limit does exist for this. It's like if I could go into the graph and fill in the hole, so it would look like this, and you have it in your notes. It's like you can come in here and go, well, if I were to fill that in, then it would work. I could get the answer. So when we get an indeterminate, like we're seeing here, through direct substitution, if I were to directly plug in the number and I see I get an indeterminate form, that is usually an indicator that we are dealing with some form of a removable discontinuity. Something here can simplify so that I could take it out. So here's where we start to talk about using algebra techniques to rewrite the expression, to remove that discontinuity so that we get something where we can actually plug in the number. Okay, so a little kind of revealing of the concept behind the curtain is this is going to lead into our discussion when we get to assignment number 4 of continuity. So we saw that there are some functions that you can plug in the number and it's the same as if you evaluated the limit. And hopefully some of you kind of already see when you can do that and when you can't. So if there's no gaps or asymptotes in the graph, then we're safe with plugging in the number. So that's what essentially solving limits analytically is going to be doing, is we're going to try to remove any sort of gaps or asymptotes in the graph by rewriting it using algebra. So in a case like this, okay, I could not plug in the 2, so I either looked at the graph or I did the table. How could I do this same problem analytically? So I could take this expression and, using some algebra, rewrite that limit expression so that I could actually cancel stuff away. So I'm going to factor the top. So remember, difference of cubes. So as I told you guys last week, that we're going to be using all the stuff that we learned from previous years. So now this is all going to come back. So we have that over. So that's me factoring the numerator. So if you see that what I wrote here in the numerator, if you're looking at that and you're like, huh? Like, what? Where'd you get that? You need to go back and review your algebra 2. So difference of squares, how to factor that. So you can look that up. Oh, sorry, difference of cubes, not difference of squares. So now I have this, and because I rewrote it, I can now see, oh, I can remove that discontinuity. So I really have is this. So now if I were to plug in the number, it's going to give me the same answer as I saw when I did it with the table and when I did it and when I looked at the graph. So I'm going to get 2 squared is 4 plus 4 plus 4 for an answer of 12. Okay, and that's how we solve a limit analytically. I'm going to use algebra to rewrite the expression, and now it's safe for me to plug in the number because I have removed that discontinuity. I canceled it away in the expression. All right, so in my next video, I'm going to go ahead and do some more explicit examples of this, showing you different algebra techniques you may want to do to rewrite expressions to help cancel away these removable discontinuities. But really the point of this video is, again, hammering home how indeterminate is different from undefined. So again, indeterminate is going to be our 0 over 0 or infinity over infinity. That's what I'm looking for when I see indeterminate.